Thank you very much. So, yes, my name is Davide Mottin. I'm an assistant professor at Aarhus University. The topic of today is about cleaning, which is a very, very broad topic, and we'll try to give a smooth introduction. So yeah, just quickly about me. Before being hired in Aarhus University, I was a postdoc in Berlin, or it's actually Potsdam, and before that, I got my PhD in Italy. And I spent a couple of research stays abroad. But enough about me. So what I'm interested in and what is my general research area is graph mining. I can describe it like that. So everything that has to do with graphs, and where graphs, as we all know, basically are networks in which nodes represent some specific entities, and there are some relationships that might be named or not. It depends on the kind of graph that you are analyzing. And we are very lucky that nowadays there has been a surge and actually an increase of graphs. So it's fairly easy to find data. That there are social graphs. Of course, they have popularized this second wave of graphs, and before there were road networks and more specialized. But there is actually quite a lot going on in biomedical applications, both from the really to the construction of drugs, to the graphs that encode patients' diseases and so on and so forth to help in hospitals. They're also used in journalism. So it's actually a very, very nice and interesting area. And my area, so my interests are around different questions. And some of them is about how to search intelligently, which is partially related to what I'm saying today. Some exploratory analysis, so how to find information if you're completely clueless of how the graph looks like. Analytics in general, so from traditional clustering, community detection, node classification. And one of the questions that it's always in the back of my mind, and I keep working on it, is about the usability. So when you have a system that answers questions to the user, like a database system, more specialized, so graph database systems, how can we actually guide and help the user? Or how can we explain maybe provenance or explainability of the results that you obtain? And the other aspects is about personalization. So how can you find answers that are better and better for the specific user? Yeah, my research is more or less in these three areas. So from data mining, databases, and machine learning. More recently, machine learning, but before it was mostly databases and data mining. So if you're interested, of course, I'm willing to talk about other things. I have worked in similarities for graphs, learning similarities, defining similarities, what it means to be similar. So either what a graph can be similar to another graph, or what a node is similar to another node. And related to this is the alignment, so to find the correspondences among different graphs. As I said, exploratory analysis of large graphs, and there it has to do really to find information when you don't know exactly what to look for and how to guide the user towards the proper information, so in an exploratory manner, and a bit of machine learning. But I want to start more towards the topic of the talk today, and I start with a quote, and this is: intelligence is an accident of evolution and not necessarily an advantage. So whenever we have to deal with something that we deem as smart, we have to ask ourselves, are really the answers that we receive correct? And this is the entire topic of today. And it has to do, of course, of how precise, how clean is your data. This was Isaac Asimov, by the way. So I think maybe you have heard of this quote, but for sure you have heard of Asimov. And my specific application is about semantic search. So currently we have quite smart ways of interpreting queries. And one of the queries in a search engine is, what is the capital of Denmark? And if you haven't been, of course, you are welcome to come to Denmark. I'm not in Copenhagen, unfortunately, but this is the answer that you obtain. So you obtain a semantic answer, and you have this box which represent some information about Copenhagen. And this is also embodied in some of the recent smart devices. We can call them recent, but there are somehow 6-7 years ago, or they started appearing, and they are very, very popular nowadays everywhere. Google Home, Alexa, and other smart devices. So one of the questions that you can ask is, what is the weather today? And just to give you a context, in Denmark always rains, so that is the answer that you will probably very often obtain. Where is Aarhus? So that is basically, it's pronounced Aarhus, is very, because this is the Scandinavian O. This is a small town and is located in Denmark. It's the second biggest city in Denmark, but that doesn't mean that it is big. Or we can ask something like, when did copyright start? Accidentally, this answer is correct if you ask now to Google, but you can also get the wrong answer. And this is one of the problems. So how can we even discriminate whether this is true or false? It's an excruciating problem, because if the data is dirty, the device doesn't have any way to say, okay, this is correct or not. But before digging into that, let me show you what happens when you ask these questions. When you ask this question, there is a mechanism that translates this natural language query into a query in a knowledge graph. A knowledge graph is a specific type of graph where each of the nodes are entities. Like in this case, this is the city of Aarhus, this is EU, this is Denmark, and the connections, the edges in this graph are semantic relationships, like member of. And with some SQL-like language, even if you haven't used any of the RDF stores, but you have heard of them, this is SparkQL or Cypher or any other language, you can get an answer very easily. So with database techniques, you can extract an answer to your question. There is a mapping, of course, from natural language here, which is also very interesting. It is mostly done by some encoding of some sort of in this site. Anyhow, you receive an answer and you're happy. Let me just formalize a bit better what a knowledge graph is. By the way, there are a lot of these knowledge graphs out there. Some of them are freely available. Freebase doesn't exist anymore. Now it's Wikidata. There is DBpedia, there is Yago. These are general purpose, and there are more specialized ones. So only for geolocations, some others that describe some specific organizations. Some of them are proprietary, unfortunately, but the idea is that a knowledge graph is a set of entities, as I said, which is indicated by the letter E, a set of relationships or relationship names, and then a set of facts or triples, and where a fact is an entity, a relationship name, and another entity. So very, very easy. Currently, we have it is very exciting to work in this area because these graphs are enormous, and you have to really invent many different methods, and the scalability is an issue for this, for finding information in such knowledge graphs. There is a problem, though, that if I have again some domain expert, is probably might not know exactly whether it is true or not. Actually, the domain expert does, but not everyone does. So what is the capital of Denmark? We have already assessed. It is possible to find an answer. But one of the questions that can be asked is Johnson vaccine used in Denmark? As the question before, what happens here? Well, it happened that the data is outdated. It's simply outdated. So there are many different types of errors. Finding them is not that easy. But there are a few methods, so there is some hope. And just to give you a dimension of how this is problematic, well, misinformation has started growing and growing and growing. So the having clean data is a must. At least this is for me something that really bothers me. So the propagation of wrong information is really a problem. These are all fake news, and there are also statistics on how much people trust in information sources. And unfortunately, the trust has been going down and down, even for traditional sources. So newspapers and media in general. Of course, it went down also for the social media, but it was not high already. But we know that the social media is much more noisy from the side of information. So let's look now of what is available for knowledge graphs. At least one of the methods that are available for cleaning knowledge graphs, and these are rules. So let me just explain a bit what these rules are. Well, a rules is basically, you can see it as a conjunctive query, basically, in the simplest form. So you have a set of axioms here that tells you, okay, there has to be some specific condition, like a fact or a relationships, from which a certain head follows. So if all the facts in the bodies are true, then it should be true also the head. An example of such a rule. So if this is a handcrafted example, so okay, maybe it could be better, but let's give an example. So if x is a variable, is part of Scandinavia, so this is Scandinavia, and x is a country, then it is also a member of Schengen. This is true. I constructed, and it's true. However, in the data, we didn't have the connection between Denmark and that is a member of Schengen. So these rules allows us to create this link. So it allows us to create and say, okay, sure, this is missing, I create something. It is important to notice that these are somehow called positive rules. So they create a new connections. However, there are also negative rules that destroy the connection, that says, okay, this is not possible. So if you have this and this and this conditions, then it is not possible that. Or if, so for instance, if you are in US, it is not possible that you are part of Schengen. Of course, negative rules are much, much more than the positive rules, and there are some challenges also to how to mine them. Anyhow, so how do we get to these rules? Well, there are two different methods for getting to these rules. The first method is manually. I write, so I'm a domain expert. I can write this rule. I know exactly that this rule is true, and I apply to the data. This is fine as long as your data is quite small, because if you have to go through an entire knowledge graph, so which comprises of organization, which comprises of all sorts of informations there, from politicians, comic books, movies, and so on and so forth, writing manually rules is really, really cumbersome. So you have to ask people, and you have to ask multiple experts. On the other side, there is the automatic rule discovery. And I will tell you a bit more in a while. So these are algorithms that look into the data and find the rules. And they're generally fast. So up to some definition of fast. So since it's not real time, so you have to let them run. But at the end of the day, and the end of the week, you will have your set of rules for your knowledge graph. They are completely data-driven. There is a problem that they might be imprecise, and they rely on data quality. Let me show you why, because this is the crux of the entire situation. Okay, so automatic rule discovery works in this. They have more or less the same framework. What changes typically is what is a rule, so what it constitutes a rule, and how to compute this confidence score that I will just walk you through quickly. The simplest of the confidence that we can think of it is the standard confidence. And it's the percentage of instances that satisfy the body over the instances that satisfies the body and the head. So it means that the support of the rule here is basically the conjunctions of the body conditions and the head condition. So how many of facts, so you basically can write this in SQL or in SparkQL, how many of these facts are true in the body and in the head. And in the denominator, we have just the body, basically the number of facts that are true in the body. So just to give you an example again with the rule, we have that the rule as before, so the part of X Scandinavia, and that is a country X, and then it is a member, X is a member of Schengen. We count how many are part of Scandinavia. They are countries and a member of Schengen. In this case, we have only Norway and Sweden here, so 2. And below you have what are part of Scandinavia and is country, which is only the body, which are part of Scandinavia 1, 2, and 3. So this is the how you compute the confidence. There is an important one that has been noted, that this standard confidence doesn't distinguish whether a fact is false or it is just unknown, because you treat them all at the same manner. So here in the denominator, you just treat everything that there is out there, but you don't know whether they are false or not. So that you still treat everything as true. So one of the popular methods for rule discovery is AMIE. I will not go through all of them, just to give you an example of how people thought about solving this issue. So they noticed that there was a problem in the confidence. And they created a PCA confidence, and this PCA confidence is not only all the facts that are true in the body, but also for which there exists a counterexample. So the counterexample has exactly the same relationship as the head, and departs from the same, basically the same entity. So that means that you have the same relationship, but something different. So connected with this, it might have multiple interpretations. So this fact does not constitute a truth, and therefore it should not be counted. And this makes the denominator more restrictive. That's good. And how do we actually find these rules? And here is exactly where the point is. So a simple algorithm goes through, generates some rules, and controls and checks whether the confidence, in this case the PCA confidence, is greater than a certain threshold. If the confidence is greater than a certain threshold, then the rule is considered valid. Which is basically, the algorithm is similar to association rule. It doesn't have much difference inside. Of course, there are some optimizations in the pruning techniques, but more or less that is the framework. There is a number of these methods, so it has been an active development. You can find, for instance, negative rules, as I mentioned before, that are rules that allows you to clean the data as removing things that are not true. There are rules with constants, as I used before with the Schengen and the Scandinavia. These are constants. So otherwise, the rule in AMIE, the rules have only variables. There are anytime methods, but all in all, they have all the same problem. So, and the problem is they have to measure a confidence in the data. If you measure confidence in the data, no matter what you do, no matter how strong you are, you either prune too much because you are really unsure, or you rely that the data has some quality, which statistically works well if the fact is very, very, very common. But that means that also this fact and this rule, it is also trivial. So if A is married to B, B is married to A, yes, sure, that's a fact, but doesn't really tells us much. So if the quality of the data is not sufficiently good, the rules are also wrong. And then you basically clean the data with the rule that is wrong. So our solution was actually to merge this world, to start and say, okay, there must be some way in the middle. We can meet in the middle. And this is what we came up with. It's a paper that we presented last year, which is called few-shot knowledge validation. So you ask the user to validate a very small set of facts, not the rule. A rule is hard to validate. A fact is much easier because a fact you can always also Google it. Okay, so let's see how we approach this problem. Well, the framework should be fairly clear right now. We have a knowledge graph, we have a set of rules, and we want to validate these rules, no matter where these rules come from. So we want to be sure that the rule, that the confidence of the rule is a real number, is a number that reflects the reality, which is might not be true because the data is poor quality. Okay, so let me just walk you through the recipe, and then I'll also show you what is the algorithm about. So the general idea is the following. So if we run the left-hand side, we obtain all the instances of A and B that talks about basically that verify these facts. And what we want to verify is to have a method that tells us which one of the produced by are actually true or false inside the database. So our thought is, okay, let's verify this fact on the right, given the fact on the left. So given the body is true. Given that the body is true, where and when is the head true? One possibility is, okay, sure, we execute it, and then we ask one by one to evaluate these facts. This is still boring, and it can be enormous. So the rules can have hundreds and thousands of results. Even the specialized rules, you might incur in 1,000 of results. We would like to do this process with a very few shots. So in a very few questions to the user. But how? Well, here is the framework that we created. So we sample a triple from the set of all the triples that are instances of the rules that we have. We ask a domain expert. We then create an embedding of this triple, which I'll show you how we do it exactly. And then we basically add to the label instances, and we have a classifier, a model, that allows us to tell, okay, this is true, this is false. So we learn true and false values for each of the triples that are verify somehow the body. Okay, so this is the recipe. This is the general recipe. How we do that? Okay, so let's start from, okay, and then we iterate this. So we keep iterating for a certain amount of time until we believe it that the quality is good enough. Okay, so the first thing is, how do I train a classifier, a general classifier? Well, maybe you're familiar, maybe not. I'll just go quickly on what we used as a technology. These are called knowledge graph embeddings. And the purpose is to embed or to transform every node, every entity, and every relationships into a point in a multidimensional space. As you can see here, Liverpool is represented by a vector in the space. A is also a vector in the space, so everything is embedded. Every single operation is embedded. This is the general idea. These are not my slides. I just borrowed from a tutorial that, if you're curious, you can look it up, and it's actually very good. From the same tutorial, so the recipe for constructing an embedding is the following. You take an input, your graph, and you have a lookup layer that basically transforms these into a sort of a vector. You have a scoring layer, or gives a number basically to each of the nodes and each of the relationships. You have a scoring layer that provides how close, if you want, so, or how likely is to see this specific triple. This is subject, predicate, and object. In some literature, it's written like that. In some others, entity one or entity tail, head, and so on and so forth. But anyhow, the important thing is that the triple is Liverpool is a city. Then you have a loss function, a learning process, and some downstream task to verify that your embeddings really work. Just to give you one example of how the embeddings works, I take the simplest one, and this is how the scoring function works. So once you understand that this, basically you can understand the whole set of the embedding methods, because they basically change, the recipe just changes the different scoring functions. So the purpose is to assign a score to a triple SPO. As I said, is the existence, so how likely that triple is actually existing. Existing probably is not the right word. It's better to say it is a true fact. One of the earliest ones was the following. So the score is given by saying, okay, I take the subject entity, I translate the subject entity by the relationship, and if I do this operation, the subject plus the relationship should be close to the object. Why this is intuitively correct is because if I have Denmark, capital of, I want that Denmark, capital of, which is my question, brings me close to Copenhagen. That's the overall idea. Once you have one of these methods, it doesn't really matter for our purpose. We have used one, we have picked one in our experiments, but once we have this, you have a vectorization of each of the entities. Now, what we have done is a quite simple operation. So we said, okay, in order to have a vectorization of a triple, which we don't have in the original version, since we don't know exactly what is the relationship between these two, or because we are still asking the user whether this exists or not, we just concatenate the two vectors together. And the other thing that we need to ask is, how can we have a similarity among triples? Well, if you are in a vector space, you can use all sorts of similarities. One of the similarities that you can use is the simple cosine similarity. Okay, so far so good. So we have now the similarity part. So that tells us whether two triples are similar. And that is important because now we need somehow to to devise a classifier that tells us, okay, given this triple, tell me if it is true or not. I go through similarities because it is a convenient way also to model the rest of the problem. So we devised the first model. The first model was, okay, sure. We look at we take the similarity measure, and for each of the triples, we define a set, and the set is the similarity among that triple and all the other triples. So the sum of the similarities among that the triple and all the other triples. That gives me basically a score for the triple that in this case represents a set, and I can do that for each of the triples. Now I want to select a number of iterations to the user. So I want to select triples that at each iteration maximize somehow or better, my first objective is to maximize the coverage over all the possible triples. So because my idea is, if I have this similarity that tells me how similar it is with respect to all the other triples, my problem can become asking the user a set of k to evaluate k triples such that I know all the rest of the other triples by similarity, because they are similar enough to the triple that I'm evaluating. This is a maximum coverage problem, and it can be solved with the, well, exactly, of course, it's an NP-hard problem, but it can be solved with the greedy algorithm, and it returns some results. And how do we classify the triples? Well, we assign the score. So we assign it is an existing or a non-existing, is a true or a false triple, to the closest, so to the label of the closest of the sets that I have been evaluating so far. Seems it is longer to say than actually to see in practice. Okay, so what is the problem with this model? The problem with this model is that it uses a fixed similarity measure. So actually we rely totally on the similarity. The similarity is telling us what is true and what is false, because then we use a K and N classifier. So the K and N classifier just knows, okay, what is the closest. Actually, a one here is a one and N classifier, not a K and N classifier. And if the similarity measure, so this is basically making an extra layer to the embedding methods that we have. If the embedding methods have learned from the data, I'm still in troubles because the similarity measure is still biased towards the cleanliness of the data. So I cannot rely completely on the similarity. And it would be better if I can learn that similarity. Well, our other approach is to use Gaussian processes. A Gaussian process is a distribution over functions. And it is a very simple thing. So it's basically, okay, I don't know where the function is. I just have a distribution of where the function goes. More precisely said, it's every point in a Gaussian process is a Gaussian. So basically, you have a distribution over the single points, and the points form by sampling in sequence these points. You form a function. You can see it in that manner. The interesting idea is that you can use some Bayesian reasoning and say, okay, I sample any of the points here, and in this case, a point is a triple in our case, and I ask the user, is it true or is it false? Well, when I ask this user, it gives me an answer, and I know that the function will go through that specific point because now it's a known fact. So the posterior basically tells me that the functions have to go through this node, this point. Okay, so I repeat this process. I can sample another point, I can sample another triple, and I ask the user. In the end, I will have a more precise distribution of where the function is. And these functions will tell me, in our case, whether a triple is true or is false. So it is not as beautiful as this. It's basically a 1, 0. So it goes dramatically up and down. But that's just an illustration. So as I said, every point is a Gaussian, and wherever you see that it is smaller, here the variance is also smaller, and you can select points. You can sample from this model. It's a Bayesian model, and there are many different ways of sampling. Usually they strike a balance between exploration and exploitation. And if you look here, exploitation is that you are close to the mean of the Gaussians, of all the Gaussians. So it basically, it passed through the means. And exploitation is that you're close, you basically take things or points which have large variance. And it could be a point here. And why should I do that? Is because I can learn a bit more. So if I do pure exploitation, I might actually end up in learning something wrong. It works fairly well. There are quite a few theorems that tells us how these processes work. Okay, I have to go a bit faster here. The bottom up is that not only we can learn through a Gaussian process, but we can even use something a bit more sophisticated called kernel learning to learn any sort of similarity by using neural networks. They're a bit harder to train, but they give slightly better results. And I don't go much into the details of this specific model. It's just basically an extra layer on top of the Gaussian processes. However, one important thing to ask is, you remember that we have to select and to ask the user some question. So how do we sample? Well, in the case of these Gaussian processes, we can sample randomly. So we have the space of the function where it is, and we just sample a random triple. We can sample with the maximum uncertainty, so where the model is more uncertain. Or we can use some more sophisticated process, which is the one that I showed you with that strikes a balance between exploration and exploitation. Okay, so I'm almost done with this enormous presentation, but let me just walk you through quickly to the experiments. So we have generated some rules using some of the known methods that I mentioned, so Rudik and AMIE, and we asked it ourselves: is our model actually able to produce better confidence scores, so than the scores that are given by AMIE and Rudik? We have selected manually 26 out of 589 rules according to different criteria. And these 26, we manually label them. So if you're interested and if you want to continue, the data set is actually available, and I can give you the slides later. But this is the 26 rules that we manually evaluated on Yago. And so you can actually create your model or your method of preference here. Just to give you what we did actually, what were the experiments about? Well, the first thing we asked ourselves, what is the best strategy? And as we just confirmed that random is a poor choice, so that in these experiments we asked ourselves, is a model actually a good idea? And it is a good idea. It turns out that UCB and maximum uncertainty works sometimes good, sometimes bad. Sometimes, no, okay, they work well, but they work sometimes one better than the other. And we pick the maximum uncertainty because it's much easier. In terms of model performances, we have tried, so this COLT MC is the first baseline that I showed, so the first model based on maximum coverage. This is our model of choice. And we have also tried with some active learning strategies, because this looks very much like active learning. And some of the common active learning methods like logistic regression and SVMs. In blue, there is variance, and you can see that at some point the variance reduces, as it should be, because this is exactly what the model is designed for. And but also that, first of all, that the maximum coverage, so using just embeddings and building on top of the embeddings, is not a good idea. Or it is actually not bad. For sure, you will reach 100% because at some point you have labeled everything. But it goes much slower. So while our method is actually quite fast in picking up, of course, there are still errors, but let's see what kind of errors. Well, to prove that, we wanted to see, okay, what if we measure the real confidence? So how far are we from the confidence? Well, it turns out that after 20 instances, we are already 10%. So basically, it's the error is double in the standard confidence. And you can look that it keeps going down and down. So our model is general enough to be able to keep improving over time. And you don't need an enormous amount of instances, so of questions to the user, in order to find the right answer. Okay, this is for today. Again, for whoever is interested, I'm also happy to discuss in another moment. Okay, this is my general area of research, but you can ask any question about doubts or curiosity about this work that I just presented.